Hello, dear students. Welcome back again in this online session. So, write your name and roll number in the comment section. So, let us wait for 1 or 2 more minutes and then we will start it. So, in the meantime, you write your roll number and your name in the comment section. So far we have discussed in detail about the liquid drop model, in which we have discussed about this independent particle model, and then we have discussed about the semi-empirical mass formula, in which we have discussed five type of different energies and their role uh, in the binding energy of these nucleons within the nucleus. We have discussed about some properties which are related with the nuclear fission, and how we can derive the relation of this z square over a. So from that we can uh, which is different for lighter nuclei and for heavier nuclei, and which successfully explain which about the spontaneous nuclear fission phenomena. So in this lecture, we will discuss what are the various assumptions which we have considered in the liquid drop model. I will write down 3 4 important points. So then we will discuss what are the major achievements of this nuclear liquid drop model, and then we will discuss what are the various failures of this liquid drop model, ਕਿ ਜਿਹਦੇ ਕਰਕੇ ਜਿਹੜਾ ਹੈ ਇਹ ਮਾਡਲ ਕਿਹੜੀਆਂ-ਕਿਹੜੀਆਂ ਪ੍ਰੋਪਰਟੀਜ਼ ਜਿਹਨੂੰ ਸਕਸੈਸਫੁਲੀ ਐਕਸਪਲੇਨ ਨਹੀਂ ਕਰ ਸਕਿਆ, ਐਂਡ ਵਾਟ ਇਜ਼ ਦੀ ਨੀਡ ਆਫ ਅਦਰ ਮਾਡਲਸ, ਕਿ ਉਸ ਤੋਂ ਬਾਅਦ ਜਿਹੜੇ ਕਿਹੜੇ-ਕਿਹੜੇ ਮਾਡਲ ਆ, ਸੋ ਜਿਹੜੇ ਲਿਕੁਇਡ ਡ੍ਰੌਪ ਮਾਡਲਸ ਦੀਆਂ ਜਿਹੜੀਆਂ ਲਿਮਿਟੇਸ਼ਨ ਸੀ, ਸੋ ਉਹਨਾਂ ਨੇ ਦੂਰ ਕੀਤਾ. So starting with the assumptions of liquid drop model. So first assumption which we have considered while deriving the semi-empirical mass formula. So I will write here some important points. Assumptions of liquid drop model. So in this model we have considered that the nucleus, it is a incompressible matter, and the nucleons which are scattered all over the nucleons in uniform matter. So the first assumption is the nucleus consists of an incompressible matter, and it is something like a viscous fluid, so something like a water or any fluid which is having some viscosity, and ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਐਟਮਸ ਜਾਂ ਮੋਲੀਕਿਊਲਸ ਜਿਹੜੇ ਆ ਜਿਸ ਤਰ੍ਹਾਂ ਵਿਸਕਸ ਫਲੂਇਡ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਬਾਉਂਡ ਹੈਗੇ ਆ, so same is the analogy which has been applied to the nucleus, and the nucleons, they are bound within the nucleus something like a incompressible fluid. So the second assumption is the nuclear force is identical for every nucleons. ਸੋ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ ਅਸੀਂ ਜਿਹੜਾ ਹੈ ਕੀ ਅਸਿਊਮ ਕੀਤਾ ਸੀ ਕਿ ਜਿਹੜੀ ਨਿਊਕਲੀਅਨ ਫੋਰਸ ਜਿਹੜੀ ਲੱਗ ਰਹੀ ਆ, so between these nucleon and it is identical, and we have neglected any sort of collisions or any sort of interaction between the nucleons ਕਿ ਉਹਨਾਂ ਦੇ ਵਿੱਚ ਆਪਸ ਦੇ ਵਿੱਚ ਕੁਝ ਵੀ ਇੰਟਰੈਕਸ਼ਨ ਨਹੀਂ ਹੈ, ਕੁਝ ਵੀ ਬੌਂਡਿੰਗ ਸਮਥਿੰਗ ਲਾਈਕ ਨਹੀਂ ਹੈ, and there is a uniform nuclear force which is ਜਿਹੜੀ ਇੱਕ ਨਿਊਕਲੀਅਨ ਜਿਹੜਾ ਆ ਦੂਸਰੇ ਨਿਊਕਲੀਅਨ ਤੇ ਜਾਂ ਜਿਹੜੇ ਨੇਬਰਿੰਗ ਨਿਊਕਲੀਅਨ ਉਹਨਾਂ ਦੇ ਉੱਤੇ ਜਿਹੜਾ ਆ ਲਗਾ ਰਿਹਾ ਹੈ। So third we have considered the nuclear force. It is saturated in nature. So saturation of nuclear force, I have explained this concept in detail, that the force it is more stronger to their neighboring nuclei as compared to the nucleons which are very much far away. So ਜਿੰਨਾ ਜਿੰਨਾ ਜਿਹੜਾ ਨਿਊਕਲੀਅਨਸ ਦਾ ਜਿਹੜਾ ਡਿਸਟੈਂਸ ਆ ਉਹ ਵੱਧ ਰਿਹਾ ਆ, ਉਨੀ ਉਨੀ ਜਿਹੜੀ ਉਹ ਨਿਊਕਲੀਅਰ ਫੋਰਸ ਆ ਉਸ ਦੇ ਵਿੱਚ ਜਿਹੜੀ ਸੈਚੂਰੇਸ਼ਨ ਆ ਰਹੀ ਆ, ਸੋ ਉਹਦੀ ਜਿਹੜੀ ਸਟਰੈਂਥ ਆ ਉਹ ਘਟ ਰਹੀ ਆ। So this is representing that the nuclear saturation of this nuclear force is directly proportional to the mass number of a nuclei, and the force it is directly proportional to a. So this represents the saturation of nuclear force. So fourth point, so which is very important, in an equilibrium state, the nuclei of atom remain spherically symmetric under the action of strong nuclear forces. ਹੁਣ ਉਹ ਕੀ ਕਹਿ ਰਿਹਾ ਆ ਕਿ ਜਿਹੜਾ we know that, so there is some sort of quantum mechanical states which present within the nucleus, and due to that, so there is change in magnetic movement or the quadrupole movement of nuclei, and with the change in magnetic movement or this electric quadrupole movement, so there is some sort of perturbation or some sort of vibrations or turbulence which is being generated within the nucleus, and which change the size of this nucleus. But in this liquid drop model, what we have assumed, so we have assumed that the nuclear forces they are symmetric, and the size of all the nucleons which are present within the nuclei, so they are completely spherical in shape. ਸੋ ਦਿਸ ਇਜ਼ ਦੀ ਮੇਜਰ ਅਜ਼ੰਪਸ਼ਨ, ਸੋ ਜਿਹਦੇ ਕਰਕੇ ਅਸੀਂ ਜਿਹੜੀ ਸਾਰੀ ਤਰ੍ਹਾਂ ਦੀਆਂ ਇੰਟਰੈਕਸ਼ਨਸ ਜਿਹੜੀਆਂ ਉਹਨਾਂ ਨੂੰ ਰਿਜੈਕਟ ਕੀਤਾ, ਐਂਡ ਵੀ ਹੈਵ ਕੰਸੀਡਰਡ ਸੋ ਓਨਲੀ ਦੀ ਸਫੈਰੀਕਲ ਸਿਮੈਟਰੀ ਆਫ ਦਿਸ ਨਿਊਕਲੀਆਈ. So these are some of the important assumptions, so it can be asked in short type questions. So what are the various assumptions of liquid drop model, and you can write these 3 or 4 important points ਕਿ ਜਿਨ੍ਹਾਂ ਦੇ ਉੱਤੇ ਜਿਹੜੇ ਆ ਅਸੀਂ liquid drop model ਆ ਉਹਨੂੰ design ਕੀਤਾ ਸੀ. And then we have further discussed our the Bethe-Vijiskar semi-empirical mass formula and the Bohr-Wheeler theory of nuclear fission. So they are completely based on these assumptions, so which has been implemented on this liquid drop model. So second, we will talk about the achievements. What are the major achievements of this liquid drop model? Achievements of liquid drop model. So the first achievements which has been explained by the very important semi-empirical mass formula. So it predicts the atomic masses and binding energy of various nuclei very accurately. So liquid drop model predicts the atomic masses and binding energy of various nuclei very accurate. So the concept of binding energy, it has been explained in detail by this liquid rock model, and ਸੋ ਉਹਦੇ ਵਿੱਚ ਅਸੀਂ ਜਿਹੜੀਆਂ ਪੰਜ ਤਰ੍ਹਾਂ ਦੀਆਂ ਬਾਈਂਡਿੰਗ એનર્ਜੀਜ਼ ਜਿਹੜੀਆਂ ਡਿਸਕਸ ਕੀਤੀਆਂ, ਸੋ ਵੋਲੀਅਮ એનર્ਜੀ, ਸਰਫੇਸ એનર્ਜੀ, then Coulomb energy, asymmetry energy and pairing energy. And ਉਹਦੇ ਵਿੱਚ we have discussed in detail ਕਿ ਕਿਹੜੀ ਜਿਹੜੀ binding energy ਆ which is strengthening the strength of this binding energy, and what energies which are weakening the strength of this binding energy, and from that we have calculated the total binding energy of these nuclei. So second important achievement is it predicts emission of alpha and beta particles from these atomic nucleus. So it predicts emission of alpha and beta particles from radioactive nuclei. So radioactivity the phenomena we have also discussed, and then we have discussed how these alpha and beta particles, so they are being coming out of this nucleus, and how this parent nucleus it get breaks down into the daughter nucleus, and how this nuclear reaction takes place. So third prediction is the theory of compound nucleus. So this theory which we will discuss in detail in fourth unit, the theory of compound nucleus. So which is based on this model explains basic features of nuclear fission. So ਉਹਦੇ ਵਿੱਚ ਜਿਹੜਾ ਅਸੀਂ ਲਾਈਟਰ ਅਟੋਮਿਕ ਨਿਊਕਲੀਆਈ ਦੇ ਲਈ ਜਿਹੜੀ ਰਿਲੇਸ਼ਨ ਹੈ that is z square over a, it is of the order of 15, and for nuclear fission for higher atomic nuclei, so that is of the order of z square over a, so that is of the order of 50 to 52. So these relation we have derived, and these are explaining the spontaneous nuclear fission. So why it is more favorable in some nuclei as compared to other nuclei. And then we have discussed the example of uranium 92-238. So why directly nuclear fission, it is not a chain reaction which starts in this uranium 238 nuclei. So these are some of the achievements. Apart from that, we have discussed about the mirror nuclei. So why some nuclei, so their isotopes, they are more stable. So most stable isobars we can find from this semi-empirical mass formulas. So these are some of the important achievements, so which explain the concept of mirror nuclei, so through binding energy. So these are some of the achievements of this liquid rock model. So next is the failures of liquid rock model. So, liquid drop model, we discussed that it successfully explained the nuclear fission and it explained about the various nuclear binding energy, so with mass number, and it gives a collective picture of this nucleus and what is happening actually within the nucleus. It failed to explain. So this model failed to explain about the nuclear spin and magnetic movements. So liquid drop model fails to explain nuclear spin and magnetic and quadrupole movements. So although semi-empirical mass formula, it explains very accurately the concept of binding energy. So, but it is more close to heavy nuclei than the lighter nuclei. So the concept of semi-empirical mass formula. So with experimental observation is more close to heavy nuclei than the lighter nuclei. So it matches the experimental results. So its theory matches the heavy nuclei results with experimental results more accurately as compared to the lighter nuclei. So it also failed to explain the low-lying excited states in nuclei, which are why they are some nuclei which are very tightly closed, some nuclei which are very widely spaced. So this liquid drop model it failed to explain this concept. So the liquid drop model predicts very closed space, very closely spaced energy levels in nuclei, so which is contradictory to some observations at lower energies. So the low lying excited states in nuclei are actually quite widely spaced. So why they are widely spaced? So it liquid rock model failed to explain these uh, why for the lower energy why some liquid atomic nuclei, so why they are widely spaced while liquid rock model it has considered that so they are quite tightly spaced. So next important point is it failed to explain certain well-known fact about the nuclei, why some nuclei which are more stable as compared to some other nuclei which are very close to their neighborhood. So it failed to explain certain well-known facts about the nuclei that why some nuclei having a certain definite number of either proton or neutron are much more stable than their neighbors. ਹੁਣ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ if you look at the examples of this alkali metals and then you can assume the example of noble gases, so it failed to explain that so why sodium it is very less stable as compared to its neighbor, that is the neon. So similarly it failed to explain why helium it is more stable than lithium. So these facts, so why some nuclei, so they are very less stable and their immediate neighbor nuclei, their stability is very high. So this further it has been explained by Shell model, and he introduced the concept of magic numbers. So magic numbers ਦੇ ਵਿੱਚ ਉਹਨੇ ਗੱਲ ਕੀਤੀ ਸੀ ਕਿ those nuclei so whose proton or neutron number it comes in that magic numbers and they are more stable as compared to other nuclei, and he gives some numbers something like 2, 8, 20, 28, 50, 82 and then 128. So why some nuclei whose proton number or neutron number having this number they are more stable as compared to the immediate neighbor nuclei, and this fact has been experimentally proved, and this we will discuss. So when we discuss the experimental evidences of the nuclear shell model, and it has been experimentally proved that so they are more stable as compared to immediate neighbor nuclei. So similarly, for example, 2 is more stable as compared to 3, or if we add these magic numbers, so 10 atomic number it is more stable as compared to 11. So this we will discuss. So when we will discuss the shell model. So apart from that, so these are some of the important points. So I have already explained about, so it failed to explain the spin of nuclei. So it failed to explain the magnetic movement of nuclei. So this is the end of liquid drop model. So we have discussed this model in very much detail, and now we will start the nuclear shell model. ਜਿਹੜਾ ਨਿਊਕਲੀਅਰ ਸ਼ੈਲ ਮੋਡਲ ਸੀ, ਸੋ ਉਹ ਜਿਹੜਾ ਆ ਉਹ ਕੀ ਕਹਿ ਰਿਹਾ ਆ, ਐਂਡ ਵਾਟ ਆਰ ਦੀ ਸਕਸੈਸ ਪੁਆਇੰਟਸ ਜਿਹੜੇ ਲਿਕੁਇਡ ਡ੍ਰੌਪ ਮੋਡਲ ਜਿਹੜਾ ਉਹ ਨਹੀਂ ਐਕਸਪਲੇਨ ਕਰ ਸਕਿਆ, ਉਹਨੂੰ ਜਿਹੜਾ ਆ ਨਿਊਕਲੀਅਰ ਸ਼ੈਲ ਮੋਡਲ ਨੇ ਕਿਸ ਤਰ੍ਹਾਂ ਐਕਸਪਲੇਨ ਕੀਤਾ. ਸੋ ਨੈਕਸਟ ਇਜ਼ ਨਿਊਕਲੀਅਰ shell model, or you can say nuclear shell structure. ਹੁਣ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ, so we all know that the extra nuclear electrons which are present in the atoms. So first I will compare this with the atomic spectra or with the atomic structure ਕਿ atom ਦੀ ਜਿਹੜੀ structure ਆ ਉਹ ਕਿੱਦਾਂ ਦੀ ਹੁੰਦੀ ਆ, and ਜਿਹੜੀ ਨਿਊਕਲੀਅਰ ਦੀ ਸਟਰਕਚਰ ਆ ਉਹ ਕਿਸ ਤਰ੍ਹਾਂ ਜਿਹੜੀ ਆ ਇਟ ਇਜ਼ ਐਨਾਲੋਗਸ ਸਿਮਿਲਰ ਟੂ ਦਿਸ ਨਿਊਕਲੀਅਰ ਸਟਰਕਚਰ ਜਿਹੜਾ ਸ਼ੈਲ ਮਾਡਲ ਆ ਉਹ ਦੋਵਾਂ ਦੇ ਉੱਤੇ ਇੰਪਲੀਮੈਂਟ ਕਿਸ ਤਰ੍ਹਾਂ ਹੁੰਦਾ ਹੈ. ਸੋ ਜਿਸ ਤਰ੍ਹਾਂ ਕਿ ਸਾਨੂੰ ਪਤਾ ਹੈ ਕਿ ਜਿਹੜੀ ਨਿਊਕਲੀਅਰ ਇਲੈਕਟ੍ਰੋਨਸ ਜਿਹੜੇ ਆ ਉਹ they are arranged in the form of nuclear shells. So something like K shell, L shell, M shell, N shell, so and so. So with the respective principal quantum number, so there are four types of quantum number: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So principal quantum number ਜਿਹੜਾ ਆ ਸੋ ਉਹਨੂੰ ਆਪਾਂ small n ਦੇ ਨਾਲ represent ਕਰਦੇ ਹਾਂ. So its number start from 1 2 3 so and so. Now each of these shells, so they has a number of subshells which are present within it. So they are characterized by different values of this azimuthal quantum number. So ਹਰ ਇੱਕ ਜਿਹੜਾ subshell ਹੈਗਾ ਆ ਸੋ ਉਹਦੇ ਵਿੱਚ ਜਿਹੜਾ azimuthal quantum number, ਸੋ ਜਿਹਨੂੰ ਆਪਾਂ L ਦੇ ਨਾਲ ਰਿਪਰੈਜ਼ੈਂਟ ਕਰਦੇ ਹਾਂ, ਸੋ ਉਹਦੀ ਵੈਲਿਊ ਜਿਹੜੀ ਆ ਸੋ that is 0 1 2 3 something like up to n-1. Now a subshell of given azimuthal quantum number, it can contain a maximum number of 2l plus 1 electrons. ਕਿ ਜਿਹੜਾ ਇੱਕ ਸਬਸ਼ੈਲ ਹੈਗਾ ਆ ਉਹ ਮੈਕਸਿਮਮ ਕਿੰਨੇ ਇਲੈਕਟ੍ਰੋਨ ਜਿਹੜਾ ਆ ਉਹਦੇ ਵਿੱਚ ਓਕੂਪਾਈ ਕਰ ਸਕਦਾ ਆ. ਸੋ ਸਬਸ਼ੈਲਸ ਜਿਹੜੇ ਆ ਉਹਨੂੰ ਆਪਾਂ ਕਿਸ ਤਰ੍ਹਾਂ ਰਿਪਰੈਜ਼ੈਂਟਸ ਕਰਦੇ ਆ, ਸੋ ਸਮਥਿੰਗ ਲਾਈਕ ਐਸ ਸ਼ੈਲ, ਪੀ ਸ਼ੈਲ, ਡੀ, ਐਫ. ਸੋ ਜਿਹਦੇ ਵਿੱਚ ਐਲ ਦੀ ਜਿਹੜੀ ਵੈਲਿਊ ਆ ਉਦੋਂ ਤੋਂ ਆਪਾਂ ਦੱਸ ਸਕਦੇ ਹਾਂ ਕਿ ਫਾਰ ਐਗਜ਼ਾਮਪਲ ਇਫ ਐਲ ਇਜ਼ 0 so then we have a S subshell, when L is 1 then we have P subshell, so and so. When L is 2 so then we have the electrons which are present in the D subshell, and when L is 3 so then the electrons which are present in the F shell. So these they can maximum accommodate up to 2 6 10 and 14 electrons respectively, so that you can calculate from this number to 2l plus 1 number of electron. Now why some atoms or some nucleus which are more stable as compared to their immediate neighbor? So now if we talk about the inert gases, so ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ inert gases ਸਾਡੇ ਕੋਲ ਕਿਹੜੀਆਂ ਹੈ. So suppose neon, whose atomic number is 10, so number of proton is 10. Argon, whose proton is 18. Krypton, atomic number is 36. Xenon, atomic number is 54. And radon, atomic number is 86. So ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ the outermost P subshells, so they are completely filled up, or the outermost subshell so which is completely filled up, while in the highest inert gas, so the first subshell ਜਿਹੜਾ ਆ so that is completely filled up with the 2s electrons. So for example ਜਿਹੜੀ helium ਆ which is the most highest stable inert gas ਜਿਹਨੂੰ ਆਪਾਂ ਕਹਿ ਦਿੰਦੇ ਆ, ਸੋ ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਨੰਬਰ ਆਫ ਪ੍ਰੋਟੋਨ ਕਿੰਨੇ ਆ, ਸੋ ਦੇ ਆਰ 2. ਸੋ ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਉਹ ਕਿਹੜੇ ਸਬਸ਼ੈਲ ਦੇ ਵਿੱਚ ਆਕੂਪਾਈ ਹੋਣਗੇ, ਸੋ ਦੈਟ ਵਿਲ ਬੀ ਇਨ ਦੀ ਐਸ ਸਬਸ਼ੈਲ. ਸੋ ਸਿਮਿਲਰਲੀ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ 2 8 10, ਸੋ ਜਿਹੜੇ ਸਾਡੇ ਕੋਲ ਜ਼ੀਨੋਨ ਦੇ ਵਿੱਚ ਕਿੰਨੇ ਆਕੂਪਾਈ ਹੋਣਗੇ, ਸੋ ਦੇ ਵਿਲ ਆਕੂਪਾਈ ਇਨ ਦੀ p orbitals. So in all these elements, so they are electrons so which are very tightly bound, and their first ionization potentials which is relatively very high. So they are electrons which are tightly bound. So je tightly bound ਹੈਗੇ ਆ, so they are completely in the form of pairs. So then it means it is very difficult to eject any electron from these atomic structure. So ਉਹਦੇ ਲਈ ਜੇ ਸਾਨੂੰ ਆਪਾਂ ਕੋਈ ਇਲੈਕਟ੍ਰੋਨ ਜਿਹੜਾ ਆ ਇਸ ਸਬਸ਼ੈਲਸ ਦੇ ਵਿੱਚੋਂ ਜੇ ਰਿਮੂਵ ਕਰਾਉਣਾ ਆ, then we have to supply a very high energy. So what does it mean? So its first ionization energy or first ionization potential, so that is very high. Now, if you talk about the alkali metals or alkali elements, so which immediately follow these inert gases, so which immediately follow inert gases. So for example, neon ਤੋਂ ਬਾਅਦ immediate ਜਿਹੜੀ inert gas ਜਿਹੜੀ alkali metal ਹੈ that is sodium, argon ਤੋਂ ਬਾਅਦ ਹੈਗੀ ਹੈ potassium. So similarly, so ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਆ ਸੋ ਤੁਸੀਂ ਜਿਹੜੇ ਅੱਗੋਂ ਲਿਖ ਸਕਦੇ ਹੋ ਚੈੱਕ ਕਰ ਸਕਦੇ ਹੋ periodic table ਤੋਂ. ਸੋ ਮੈਨੂੰ ਜਿਹੜੇ ਦੋ ਦੇ ਨਾਂ ਪਤਾ ਹੈ. Now if you compare these inert gases with alkali metals, so ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ ਕੀ ਆ ਕਿ there is one electron which is present in the last atomic orbitals. So ਉਸ case ਦੇ ਵਿੱਚ for example sodium ਦਾ ਜਿਹੜਾ atomic number ਹੈ it is 11. So one electron which is present in this last s subshell. So ਇਹ ਜਿਹੜਾ one electron ਆ then it is easy to excite or to remove this electron from this subshell. So that's why their first ionization potential ਜਿਹੜਾ ਆ alkali metals that is very less. So ionization potential or ionization energy required to eject this electron from this last unpaired subshells ਦੇ ਵਿੱਚੋਂ, so it is very less. So we can easily remove this electron from the subshells, and when you compare the graph of this alkali metals with respect to inert gases, and from that you can see that so they are very less stable. So something like, so if this is of helium, so this is of lithium, so this is again of neon, so this is of sodium, this is of potassium. So it is something like this. So this is of argon, this is of krypton, and this is of xenon. So this side it is representing the ionization potential. So just after the helium, so the ionization potential of this alkali metal, it is very less. So what does it mean? So they required a very less energy. So once they eject this electron and then they come into the stable form. So that's why so their stability is very less as compared to these inert gases. So these are some strong reasons to believe that, so as in the case of binding energy of electrons which are in the atoms, so similarly if we compare this atomic model to this nuclear model, so we will apply the same assumptions. The nucleons in the nuclei, so they are arranged in something like this discrete shell structure. So nucleons, so ਉਹ ਵੀ ਜਿਹੜੇ ਆ ਇੱਕ discrete shells ਜਿਹੜੇ ਆ ਉਹ nucleus ਦੇ ਵਿੱਚ present ਹੈਗੇ ਆ. So ਉਹ ਜਿਹੜੇ ਸਾਰੇ nucleons ਹੈਗੇ ਆ, so they are something occupied in this form of discrete shells. So ਸਭ ਤੋਂ ਪਹਿਲੇ ਜਿਹੜਾ ਆ ਇਸ ਜਿਹੜਾ nuclear shell model ਆ, so it has been explained by W.M. Alhazen in 1933. So he was the first to point out, who gave some points by comparing this atomic model with the nuclear model, and later M. Mayer in 1948, and independently 3 authors, Axel, Jensen, and Suez, so in 1949. So they showed that the nuclei containing the following number of protons or neutrons, so they exhibits very high stability. So they gave a number, so that the proton or neutron, so which is having this number of protons or neutrons, so they exhibit very high stability as compared to other nucleons, so or neutron or protons, so to their nearest vicinity. So they popularly gave the name to these above numbers as the magic numbers. ਸੋ these are ਸੋ ਜਿਹੜੇ ਸਾਡੇ ਕੋਲ ਨਿਊਕਲੀਅਸ ਜਿਨ੍ਹਾਂ ਦੇ ਵਿੱਚ ਆਈਦਰ ਪ੍ਰੋਟੋਨ ਦਾ ਨੰਬਰ ਜਿਹੜਾ ਹੈ ਇਹਨਾਂ ਨੰਬਰ ਦੇ ਵਿੱਚੋਂ ਹੈ ਜਾਂ ਜਿਹੜੇ ਨਿਊਟਰੋਨਸ ਦਾ ਨੰਬਰ ਜਿਹੜਾ ਹੈ ਸੋ ਉਸ ਨਿਊਕਲੀਆਈ ਨੂੰ ਆਪਾਂ ਕੀ ਕਹਿ ਦਿੰਦੇ ਆ ਮੈਜਿਕ ਨਿਊਕਲੀਆਈ ਕਹਿ ਦਿੰਦੇ ਆ ਸੋ ਦੀ ਨਿਊਕਲੀਆਈ ਵਿਚ ਇਜ਼ ਹੈਵਿੰਗ ਆਈਦਰ ਪ੍ਰੋਟੋਨ having this number or neutron having this number, so they are known as the magic nuclei. So there are some of the nuclei which is having this both proton and neutron number, so ਜਿਹੜਾ ਆ ਉਹ ਮੈਜਿਕ ਨੰਬਰ ਜਿਹੜਾ ਹੁੰਦਾ ਹੈ ਮੈਜਿਕ ਨੰਬਰਸ ਜਾਂ ਡਬਲੀ ਮੈਜਿਕ ਨਿਊਕਲੀਆਈ ਕਹਿ ਦਿੰਦੇ ਆ apart from that, so there are some atomic numbers, so there is a semi magic number. ਸੋ ਉਹ ਵਾਲਾ ਨੰਬਰ ਸੋ ਜਿਹਦੇ ਵਿੱਚ ਆਈਦਰ ਪ੍ਰੋਟੋਨ ਔਰ ਨਿਊਟਰੋਨ ਵਿਚ ਇਜ਼ ਹੈਵਿੰਗ ਦਿਸ ਵੈਲਿਊ ਸੋ ਉਹ ਜਿਹੜਾ ਨੰਬਰ ਆ ਸੋ ਉਹਨਾਂ ਨੂੰ ਆਪਾਂ ਸੈਮੀ ਮੈਜਿਕ ਨਿਊਕਲੀਆਈ ਜਿਹੜੇ ਆ ਕਹਿ ਦਿੰਦੇ ਆ ਸੋ the nuclei which contains magic number of protons or neutrons, so for example this helium, why it is more stable, because it has 2 protons and 2 neutrons, which is a magic number. So similarly, why oxygen it is more stable, because it is having same number of protons and same number of neutrons, so which is again a magic number. So why calcium it is more stable, so that is the proton and neutron number is 20. So apart from that, so one other isotope calcium, so that is 2048, so ਜਿਹਦੇ ਵਿੱਚ proton number 20 है, neutron number 28 है. So while that it is the most stable, having a very half life of around 16 years, so it is having 82 protons and 126 neutrons, so both the numbers, so they are the ਮੈਜਿਕ ਨੰਬਰ. ਸੋ ਇਹ ਸਾਰੇ ਨਿਊਕਲੀਓਨਸ ਜਿਨ੍ਹਾਂ ਦੇ ਵਿੱਚ ਪ੍ਰੋਟੋਨ ਤੇ ਨਿਊਟਰੋਨ ਦੋਨੇ ਜਿਹੜੇ ਨੰਬਰ ਉਹ ਮੈਜਿਕ ਨੰਬਰ ਹੋਣਗੇ ਸੋ ਉਹਨਾਂ ਨੂੰ ਆਪਾਂ ਨੰਬਰ ਸਟੇਬਲ ਐਜ਼ ਕੰਪੇਅਰ ਟੂ ਦੀ ਮੈਜਿਕ ਨਿਊਕਲੀਆਈ. ਸੋ ਫਾਰ ਐਗਜ਼ਾਮਪਲ ਦਿਸ ਇੱਕ ਨੰਬਰ ਪ੍ਰੋਟੋਨ ਦਾ ਜਾਂ ਨਿਊਟਰੋਨ ਦਾ ਉਹ ਮੈਜਿਕ ਨੰਬਰ ਦਾ ਹੈ ਸੋ ਡਬਲੀ ਮੈਜਿਕ ਨਿਊਕਲੀਆਈ ਜਿਹੜੇ ਆ ਕੰਪੇਅਰ ਟੂ ਦਿਸ ਸਿੰਗਲ ਮੈਜਿਕ ਨੰਬਰ ਨਿਊਕਲੀਆਈ. Now what are the various experimental evidences so which comes in line, so which explain about the successfulness or the stability of these nuclei, and on the basis of this experimental evidences, so the shell model it has been explained. So the experimental evidences for nuclear shell model. So single particle nuclear shell model ਜਿਹੜਾ ਹੈ ਅਸੀਂ ਆਪਣੇ ਅਗਲੇ ਲੈਕਚਰ ਦੇ ਵਿੱਚ ਡਿਸਕਸ ਕਰਾਂਗੇ, but we will discuss some of the main important evidences so which explain this existence of this nuclear shell structure within the nuclei. So first one is the nuclei which contain magic number of protons or neutrons, so they show very high stability. So O wale nuclei, so nuclei containing magic number of proton or neutron show very high stability. So compared to nuclei containing one more nucleons of similar kind. So the experimental measurements show that the separation energy of a neutron from a nucleus or a proton from a nucleus, so containing this magic number of nucleons, so the separation energy is very large as compared to the nucleus which is containing one or one more proton or neutron. So what is this separation energy? So separation energy is the minimum energy required to separate one neutron or one proton from a nuclei. So the separation energy is very high. So separation energy is very high for such nuclei. So second is the naturally occurring isotopes whose nuclei contain magic number of neutrons or protons have greater natural abundance ਕਿ ਉਹ ਵਾਲੇ ਨਿਊਕਲੀਆਈ ਸੋ ਜਿਨ੍ਹਾਂ ਦੇ ਵਿੱਚ ਮੈਜਿਕ ਨੰਬਰ ਦਾ ਪ੍ਰੋਟੋਨ ਹੈ ਜਾਂ ਨਿਊਟਰੋਨ ਹੈ ਸੋ ਉਹਨਾਂ ਦੇ ਜਿਹੜੀ ਅਬੰਡੈਂਸ ਹੈਗੀ ਆ ਨੇਚਰ ਦੇ ਵਿੱਚ ਉਹ ਜ਼ਿਆਦਾ ਹੈ ਐਜ਼ ਕੰਪੇਅਰ ਟੂ देयर ਅਦਰ ਆਈਸੋਟੋਪ so the natural occurring isotopes whose nuclei contain magic number of neutron or proton have greater relative abundance. So for example, the isotope of this Sorentium, so whose having number of neutron which is equal to 50. So similarly, selenium, so 140 who having neutron which is equal to 82. So they have relative abundance of 82% and 82% and 88% in nature. So ਇਹਨਾਂ ਦੀ ਜਿਹੜੀ relative abundance ਹੈਗੀ ਆ it is more as compared to their isotopes so which is having not neutron or proton with magic number. So similarly the number of stable isotopes of the element who has having magic number of proton so ਉਹਨਾਂ ਦੀ ਵੀ ਜਿਹੜੀ stability ਹੈ that is the natural abundance है it is large. So for example calcium, so where Z is equal to 20 have 6 stable isotopes compared to 3 for argon. So although argon which is very close to this calcium but calcium ਦੇ ਜਿਹੜੇ ਹੈਗੇ ਆ so isotope ਜ਼ਿਆਦਾ number ਦੇ ਵਿੱਚ ਆ and they are more stable. So similarly you can see ਜਿਹੜਾ 10 ਹੈ 10 ਦਾ ਜਿਹੜਾ atomic number ਹੈ titanium whose having atomic number which is equal to 22 so which is close to calcium so it is having 5 isotope. So calcium the ਜਿਹੜੇ isotopes are so they are larger as compared to their immediate neighbors. So similarly 10 having 50 protons has largest number of stable isotopes. ਸੋ 10 ਦੇ ਜਿਹੜੇ ਕਿੰਨੇ ਨੰਬਰ ਆਫ ਆਈਸੋਟੋਪਸ ਹੈਗੇ ਆ, ਸੋ 10 ਆਈਸੋਟੋਪ, ਸੋ ਐਜ਼ ਕੰਪੇਅਰ ਟੂ cadmium, so with 48 atomic number, who has 8 number of isotopes, and the tellurium with 52 atomic number, so who has again 8 number of isotopes. So these are some of the experimental calculations which shows that, so those nuclei which is having either a magic number proton or magic number neutron, so they have more stability as compared to other, and they have more number of isotopes as compared to their immediate neighbors. So similarly, the number of naturally occurring isotones with magic numbers is usually large as compared to their immediate neighborhood. So isotones ਕਿਹੜੇ ਹੁੰਦੇ ਆ, ਸੋ ਜਿਨ੍ਹਾਂ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਨੰਬਰ ਆਫ ਜਿਹੜੇ ਨਿਊਟਰੋਨਸ ਹੈਗੇ ਆ, ਸੋ ਉਹਨਾਂ ਦੀ ਜਿਹੜੀ ਵੈਲਿਊ ਜਿਹੜੀ ਆ ਉਹ ਵੀ ਸੇਮ ਹੋਏ. So apart from that, the nuclei with magic numbers of neutron or proton have their first excited state at higher energies, having very high value than in the cases of neighboring nuclei. So I will also write the fifth point. So number of naturally occurring isotones with magic numbers of neutrons is usually large compared to their immediate neighborhood. So for example, the number of stable isotones of number of neutron when n is equal to 82, it is having 7 stable isotones, so as compared to n80, who is having 3 isotones, and n is equal to 84, who is having 2 isotones. So these are some of the important experimental evidences. So they have calculated for all those nuclei which is having this magic numbers, and they have calculated the value for the immediate neighbor nuclei, and they comes to the conclusions that, so the nuclei which is having this proton number or neutron number having this magic number, so they are more stable, so more natural abundance, more number of isotopes, more number of isotones, so as compared to their immediate neighbors. So these are some of the strong experimental evidences which comes and which support this shell model. And in our next lecture, we will discuss the single particle shell model using the simple harmonic oscillator potential, and then we will discuss the various
alert from Microsoft PowerPoint.
So we will discuss the various applications of this nuclear shell model, which explain about the concept of parity, which explain about the magnetic moment, the quadrupole movement, and how we can calculate all those values from this shell model. So Okay, dear students, I will send you a link and then you can mark your attendance over there.